not allowed. You can't have both v and y being empty string. Question mark. All right. Okay. So you can just see visually, the string here is cut into 5 pieces as a result of these r's are disappearing due to the parse tree regions, right? So this is the bottom line, so to speak, the substring x that gets generated by this r, and this substring here is generated by this r. So there'll be a bit before the x, call that v, and there'll be a bit from this one, and you'll have a substring here to the right of this x, and we'll call that y, and so on. So you can just see visually the 5 regions, the 5 parts of your string s. Okay, so the second and fourth part can be pumped. So like VV, YY. Okay, and you can see because from these r's, they're the same r, they're the repeat variable, and the grammar just each time it gets an r, you can generate a subtree, because it's what grammars do, right? So therefore, this pump string uv to the I, x, y to the I, and remember there's many copies of v as there are copies of y. They have to be the same. Right? That just comes from repeating this. So uvi, x, y, I, z, that will also belong to the language. And if I is naught, that would correspond to this case. But I'm puzzled. Oh, you can't see it. This condition 2 is that the length of vy has got to be positive. That strikes me as a bit puzzling. So something for you to think about, and me as well. All right, now how to get all 3 conditions. So we're leading in now to the actual proof. So that what I've just given you was the outline, the proof idea, as Sipser talks about it. Okay. So we'll try to actually prove what the pumping length p should be for this, for a context-free grammar. Okay, so let's see. Most of this square is involved in the reasoning behind the idea that long string, that long path, the long string, and hence a long path, must have a repeated variable, which we called r, big R. Okay, so that's what this is. Okay, so the formal proof, the actual proof, the details. Okay, so that big G, that's the grammar. Okay, your context-free grammar for a context-free language A. Okay. Language is context-free if there's a context-free grammar G that derives it, that generates it. But what's a context-free grammar? That still hasn't been spelled out fully. Informally, it's when the left-hand side has only a single variable. But I'm getting ahead. Okay, right. Okay, now a couple of you go looking at all the rules. Have a look at all the rules in your grammar, okay? And find the maximum number of symbols in that right-hand side. So so you go to your grammar, you have a list of all the substitution rules, have a look at all of them, and for each one, calculate how many symbols the right-hand side of the rule has. And then find this number little b, which is the maximum number of symbols in these rules, the right-hand side of these rules. Okay? So that's your little b. All right? Now, we're going to use that. We're going to play with this idea for quite a while, and with it, deduce that there has to be a repeated variable down the path from the start symbol to the terminal symbol, down that derivation path in your parse tree. Okay. Right, so we now know what little b is. It's the maximum number of symbols in your rules on the right-hand side of your of your rule. Okay. Now, so that means if you have a particular node in your parse tree, parse tree is just a graph. Okay. Go back to chapter 0. So now if little b here is the maximum number of symbols on the right hand side of your rule, then a node will have at most b children. What's a child? Well, you have a node, and you'll have edges to other nodes, right? The other nodes, they're children, because they have edges connecting to the parent node, right? So a parent node, if you like, will have at most, right, that's equal to b, little b children, right? Well, and that has to be because we chose little b to be, the maximum number of children in a rule, if you like. Okay. All right. So if your parse tree just has def 1, so you start here at the start symbol, and then you have all terminals, so effectively you have like one rule, and so if your parse tree consists of just like one step, 2 layers, like the upper node is the start symbol, and all the bottom, they're all terminals. That would be the right hand side of a rule, and so the number of children, or they're leaves because they're terminal symbols. It'll have at most b leaves in one step. Okay. Now I have a parse tree that it's 2 steps. So you have your last leaf will be found at the second step, right? Now at most. Now each. So here's your start node, your root node, and then step 1, step 2. So the second, that's your first layer. So the second layer, at most, you'll have b edges coming out, right? And then from each of those, at most, you could have b edges. So the maximum number of nodes, that'd be terminals, at the second step, the third layer, if you like. So the first layer, that's the root node, and then the second layer, at most you'll have b of them, and at the third layer, at most you'll have b squared. Okay, leaves at most. So b squared. So generalizing this idea, if you now have a parse tree that has h steps, so it'll be like h plus 1 layers, then the maximum length of your string at the bottom, maximum number of nodes at the bottom, would be, so we have h steps, okay? So the maximum number of nodes at the bottom would be b to the h, right? We had b, and we had 2, starting from the top node, the root node, then one step down, maximum b leaves. And if your parse tree has like three layers, but 2 steps, then the maximum number of nodes or leaves would be b squared. So that's with like 2 steps. And if you have h steps, then you'll have b to the h. That'll be your maximum length of your nodes at the bottom, maximum. And they'd be terminal symbols, right? So your b to the h. So that means, and we'll use this later in the proof, but it's interesting. If the string that you generate has this length, if it's larger or equal to b to the h plus 1, okay, plus 1, then the height of the string, in other words, the number of steps, right, the height of the string, same thing, must be at least h plus 1. Right? Can't be h. If it were h, the longest the string at the bottom could be would be b to the h. But this one's one longer than that, and therefore you must have how many steps? You must have at least h plus 1 steps. Okay, now that's critical for proof later on in showing that there has to be a variable that gets repeated down that long path. So we'll use this. Okay. Now, just this last little bit before I sign off for this session. Let v, well, mod v, we'll let this symbol here. That's the number of variables in your grammar. Okay. This here, mod, double bar with a v. V is the set of variables. So this double bar tends to mean size of. Okay. So if the number of your variables in your grammar, let it represent that by this symbol. Okay. So I'll just call it mod v. So mod v is the number of variables you have in your grammar big G. Okay. And we'll use this in the next session as well. It's part of the proof that there must be a variable that gets repeated as you go down the path.